We'll go over how to use the program MOTE, the measure of the effect. It's available for free at aggieerin.com. That's aggieerin.com/MOTE, M-O-T-E. And this software will help you calculate effect sizes for several different types of tests, as well as give you the confidence interval for the effect size should you be working on a meta-analysis or you just want to include it. So the benefit to the program is that it calculates non-central confidence intervals for effect size. So these are not your standard centralized confidence intervals like you would calculate on a mean. And which Cumming has shown that and Smithson, that they tend to be very skewed distributions. So this will calculate it based on that non-centrality parameter. The other benefit is that sometimes you can check and make sure you have your test statistics correct. Not in all of these, but in a lot of them. Future updates will include p-values for the test statistic when appropriate, and some of the non-working windows that I'll show you in this video are being updated now. So to start, I'm going to start with a z-test. These are fairly simple tests to calculate by hand, as well as the effect size by hand, but if you're like me and bad at a calculator, maybe you want to do it on the computer. And so a z-test has a Cohen's d as its most popular effect size, and instead of calculating the test statistic with standard error on the bottom, you calculate effect size by using standard deviation on the bottom. So in this sort of design, you will have a population mean and a population standard deviation. So an example might be if you were comparing to a standardized test score. Okay. So you can calculate from the mean directly or from a z statistic. And so there's two different ways to do this. And then I've given some output over here. Examples from SPSS, the descriptive statistics that you would get from SPSS, and from SAS. Now in the MOTE window, when you open it, what you'll get is the screen for z-test. It's the automatic one that opens up, and it includes several numbers to start, and that is simply so that we're not dividing by 0. So the main theme for working in MOTE is that you have to enter always have to enter n, because otherwise it's going to calculate based on 2 participants, and that's just so that we don't crash the program in the background with the math. Okay. So you've got over here on the left side, you always will have numbers to input, and the inputs are always labeled as inputs, so you don't have to enter all of these, but you have to enter enough of them to get a number. And so generally that's going to be a mean, some sort of standard deviation or error, and n or degrees of freedom. Okay. The results down here are things that you can't change. Okay. So it is giving you the Cohen's d value and its confidence interval, and this deviation number is based on confidence here. So if I changed my confidence interval to a 99, so it's 1 minus alpha, so if you set p less than 0.01, it would be a 99% confidence interval, that deviation score will correspondingly change. So you cannot type down here at the bottom because you can't change those numbers. They're based on these numbers up here at the top. Okay. The other things you can do is reset the data. Okay. So my printer is going nuts for fun. So that will clear out numbers that you've entered. And then the measures column is where all the different options are. And I'll walk through the first couple of these in this video. So I'll go all the way down through Glasses Delta. And these will be covered in another video once they're perfected. They work okay right now, they're just not perfect. And then we're also adding chi-square, and then odds ratio 1 does work. Help will take you to this user's guide, and About will take you to all the code provided on GitHub by our fantastic programmer named Tim, who has really been a wonderful asset to this project. Alright, so let's start with Z. If I had this SPSS output or this SAS output, therefore the same data, I would know that I have a sample mean of 12.8, so the sample mean goes here. Okay. I don't have the population mean yet because I haven't shown you the example, but I also know that I have at least 30 people, so I'm going to put that in under N. Okay. So what happens is when you enter a number that is tied to another one, so n and degrees of freedom are tied together, so degrees of freedom is n minus 1, it will automatically update the other number. So if I had written 30 here, it will automatically fix the one above. So make sure you're in the right spot when you're entering numbers, and also know that the other ones will change accordingly. Well, that's why it's so important to enter n, because standard error is calculated based on n, and so if you leave it as 2, which is the auto default, it will calculate the wrong number for you. Okay. And so from the output, I could pull my n as 30 under here, and my sample mean here if you were calculating it from a big set of numbers, or if you're in SAS, n is 30, and the mean is under mean. So for an example, let's assume our population mean is 10. So I'm going to come up here and go to 10. Now one quick thing is you can double click and backspace and hit enter, or you can just, if it's blue like this, you can just type on top of it. So you don't have to double click on them to get rid of them. And then let's say our knowledge of effect size scale, so we gave a scale to students and asked them what they knew about effect size. So they scored a 10, and then our standard deviation, or sigma, is 2. Oops. Wrong window. Come over here, and it is 2. Okay. Now, when I entered 2 there, you saw that the standard error auto-calculated, and it's based on the sample size that I had put in. So that would be sigma m if you're doing a basic stats book, or just standard error is where we generally think about it. And that would have given me a z statistic of 7.67, which is a gigantic z number, so my examples are always the best, but it basically is 12.8 minus 10 divided by 0.37. Okay. And then it also auto-calculated Cohen's d down here at the bottom. So I would have gotten a 1.4 effect size, that's large, and then the confidence interval is ranging from a negative 2.5 to a 5.3. So that confidence interval covers 0. So while this is a large effect size, I should be a little skeptical because it does cross 0. But one problem with the z statistic is that the confidence intervals often will cross 0 because of the way they're calculated. So this is sort of based on a normal distribution because z is supposed to be not supposed to be normal. Not supposed to be non-normal. Blah. Okay, so it's based on using this deviation score. So it's adding and subtracting 2 standard errors times 2 standard errors. Or maybe it's, no, 2 standard deviations. Sorry. All right. The other thing that happens is that you get the picture will update. Now these pictures are totally editable and savable. So you can zoom in and zoom out. You can fix the range of them if it goes off screen. You can change their properties like the color. You can change X and Y axis labels. There's actually more options for the graph than there is to enter effect size, but you can edit these pictures if you wanted to use them. So I could change all the different colors and I can make it look crazy, but it also gives you the confidence interval up here and makes you a pretty picture. Okay. So that's how you would do one for a Z test. Let's say we wanted to move on instead to a single sample t. So now we have the population mean, but no population standard deviation. So this is a little more of a situation you might run into. So let's say I wanted to calculate the difference between scores that I have seen a ton of times in my lab, but I don't want to assume that that's the population standard deviation, and then the scores from this one semester. So I'm going to change this under measures to single sample t-test. And then we'll get a very similar looking input window. So I get the basic same idea here, but now I have t statistic. And then also a new pretty graph with 2 separate distribution curves, one for the population and one for the sample. Okay. And if you're looking at output in SPSS, you can calculate either from t or from the means. I always recommend calculating from the means and standard deviations if you have them, because those numbers are more accurate, especially when you get to independent t, because calculating from the t statistic is just an estimate. But if all you have is t, because you're doing this from a meta-analysis from different research papers, you can't actually calculate directly from t as well. So let's check here. So if I have SPSS or output from SAS, I have them all labeled. I could use, let's use this example. That's down here. So let's say I have a population mean of 7, and I want to know the difference between the population and my sample. So I'm going to scroll up here, and that's what numbers we used in SPSS. So I have 35 people. Let's leave this screen up here. There we go. Okay, so N is 35. So I'm going to change that here. And that auto-changed my degrees of freedom, which are also 34 right here. And then my sample mean is 5.89. My population mean is 7, because I knew that from my example. The sample standard deviation is 2.61. And you'll see that it gave me the same standard error as I have out here in SPSS, or standard error here in SAS. I could have entered standard error first, and it would auto-calculate standard deviation. So you always have to enter at least one of those, unless you're calculating directly from the test statistic. Okay. It auto-calculated the test statistic for me, so I got negative 2.51. That is very close to what t is over here, because I didn't use all the decimals. If I had put in 4 decimals, the answer would be much closer. And then or t down here, 2.53 rounded up in SAS. Okay. I left it as a 95% confidence interval, so Cohen's D is 0.42, which is close to medium, which is 0.5, and the range is from 0.08 to 0.77, which does not cross 0, so we would say that this is a greater than 0 effect size. And then it gives me my 2 different distribution curves. So it's calculating it based on a non-central t distribution. And so here is my Cohen's d, where these 2 distributions do not overlap, which is the definition of Cohen's d. And then it gives me a range of possible options given the values you've entered for the sample mean, standard deviation, and the population mean. Okay. It also actually gives you the upper and lower non-centrality parameters that are used to calculate these. So the math is all provided on GitHub if you really want to see what's going on in the background, but it does tell you directly what the numbers were used to calculate the upper and lower limits. And so this is how non-central it is. A non-centrality parameter, if the things are perfectly normal, it will actually calculate it based on the non-centrality parameter if they were normal. Again, you can change all these charts. Let's give it some ranges there. I can change the colors, I could save it. Let's say instead you didn't have your means and standard deviations, and instead you just had t. So I could enter negative 2.56. When I do that, it clears out all the rest of the data because they're incongruous now. Even though they're calculated on the same numbers, because those numbers, ooh, I did that wrong. 2.526. Sorry, there we go. Because those numbers aren't auto-calculated, it automatically clears them out so that you can't make a mistake. Let's throw in my negative here. Give me my negative. There we go. And so I get approximately the same numbers, calculating it directly from t. Again, the more decimals you enter, the more that they'll match. And so that's single sample t. Now, if I have, scroll through here, dependent samples t, this is where it gets tricky. Okay, there are actually 2 different options for dependent t based on some research by Jeff Cumming on the different types of denominators for Cohen's d on dependent t. So we've included both of them so that you could pick. Dependent t averages is based on averaging the standard deviations of the 2 different levels on the bottom. So here, let me go over here where the formulas are. So it calculates the mean difference on the top, which is how dependent t is calculated, time 1 minus time 2. And then instead of the bottom being based on the standard deviation of the difference scores For this type of Cohen's d, they're based on the average standard deviations divided by 2. The theoretical idea is that this is going to be a better estimate of the population effect size, because we aren't going to overestimate using the difference scores. And so if I create an average standard deviation on the bottom, that will be usually larger than the standard deviation of the difference scores. And so therefore the estimate of effect size tends to be smaller. And you'll see that in this example. So this is sort of the fix for the fact that standard deviation, the normal version of Cohen's d, overestimates population standard deviation. The other version is the standard deviation of the difference scores on the bottom. And I think the reason that people like this one is that it's based on the test statistic. So for all of the other types of effect sizes, the denominator is only the square root of n away, or something very close to that, from the test statistic, like z or t. So when you're going from a z-test with standard error on the bottom to a z Cohen's d, the only thing you're doing is going from standard error to standard deviation. If you're doing a single sample t, you're going from standard error as the denominator to standard deviation as the denominator. And so the tricky part is, with these two examples, yes, this one might be a better estimate of population standard deviation, but this one is actually based on the test statistic. So they each have their pros and cons, and I would suggest using either one, but being clear which one you're using. So using D and then like underscore or subscript averages, or D differences, and just making it clear I'm using this mathematical formula, because right now in the literature it's not clear which one people are using. You can also calculate directly from T. If you calculate directly from T, you are getting this one, where standard deviation of the differences is on the bottom. So for T averages, you'll see that it derives a T statistic, and you can't type here. So it won't let you calculate from T in this window because you can't mathematically do that. And so the derived one is just to give you the number so that we can calculate Cohen's d, and so it gives us where T should be lined up. It will not match your output because it's being calculated with average standard error on the bottom, which is not the way that dependent T is normally calculated. All right, so for this example, scroll past it here, we're looking at the differences between time 1 and time 2. And so we've given you the output here for time 1 and time 2. It's a little small. Let's make it bigger. There we go. In SPSS and in SAS. So I'm going to enter this from SPSS. So I can enter the means directly, so 5.93, 6.09, oops, 5.93, 6.09, there we go. And it auto-calculates the mean difference for me, so this is subtracting. If you're going to do dependent T averages, you're going to use this first box here and calculate from standard deviation or standard error, either one, directly. Okay, so I'm going to enter my standard deviation, 2.67, 2.64. So you'll notice that it's calculated standard error automatically, but that doesn't match my output over here of 0.39, and it's because I haven't fixed n. So n in our example here is 46. Okay. Now these should match 0.39, 0.39, 0.38, 0.38, great. Okay. T statistic won't match, so if I go over here and look at T, I got 0.49. Now it's close. A lot of times they'll be very different. It kind of depends on the example. But this is D averages, so it's going to look a little different. Okay. The Cohen's D for this example is negative 0.06. The confidence interval crosses 0, so I would say that that's small and essentially 0. And then it gives you that range of scores here between the population, or yes, this is dependent T, time 1, time 2 distributions. Okay. All right. Now let's say I wanted to instead, let's look at the SAS output real quick. Okay, so I got my means here, my standard deviations here. You can also look at mean difference here, so I could have just entered the mean difference. So let's see, mean difference is negative 0.15. and then it'll actually let me get to approximately the same number. So I didn't need the 2 times, but you could enter it either way. And then, so basically you would need the means here and the standard deviations. Instead, let's go to measures and then SD difference and look at how different these 2 numbers are. Okay. So from this one, you can calculate it based on time 1, time 2, and then it auto-calculates mean difference, but you'll notice that there's only one type of standard deviation. Okay, so for this one, the easiest thing to do is to get it from the t-test box. So I'm going to enter my negative 0.15. Okay. And then my standard deviation, the difference is 2.11. So down here, because there's only one, where there's 2 up here, this is 2.11. That's auto-calculated standard error, which is not right because I need to change n to 46. Now 0.31, 0.31, pretty close. Okay. And so now my t statistics will match. Negative 0.48, negative 0.49, very close. And you'll notice that t has hopped up here into the window where I can use it as a calculator, because on this one you can backwards compute from t. Okay. So I got a negative 0.07. But it's pretty close to my negative 0.06. The bigger the difference between the standard deviations, I think the larger you'll see that the d averages and d different are different effect sizes. So I've done some examples in my class where one of them is 0.5 and one of them is 1. So it really kind of depends on what kind of sample you're working with. If the difference scores are all approximately the same, your standard deviation of those different scores will be very tiny, but the standard deviations might be large. So that's an example of where if everybody's score went up 4 points, the difference score deviations are small, but if the standard deviation of the regular score was 5 or 6 points, you're going to get very different effect sizes. Okay. I can auto-calculate from t as well, so I can do negative 0.49 and get approximately the same number, and you'll notice everything has cleared out because I entered a number that was calculating from everything else. And so that's the 2 types for dependent t. The next thing we've got is independent t, and there's 3 types for independent t. And so let me go over what those things are real quick. And you'll notice under measures, you've got Cohen's d for independent t, and then we're going to skip d to r real fast, and then do Hedges g and Glasses delta, and I'll come back to d to r. Okay. So Cohen's d for independent t is the sort of traditional effect size version, and then there are 2 alternatives. And so it's calculated with pooled standard deviation on the bottom, so mean 1 minus mean 2 over S pooled, whereas the test statistic is calculated with standard error on the bottom. Okay. So S pooled is the average standard deviation, but weighted by the number of people in each group. So if you have an equal number of people in each group, this is actually just an average. But if you don't, this will help estimate based on the larger standard deviation that you have. You can also calculate by using this formula, although it is a little messy. It does not, it's not the best estimate. If you only have t, that's your only option, go for it. But if your n sizes are drastically different, this will, I think, slightly overestimate t, or I can't remember. I think it slightly overestimates t. I'm sorry, not t. Cohen's d. And so it is problematic to use this formula, but it is an option if those are the only numbers that you have. You can also calculate t, and if I have n, it will calculate based on sort of backwards computing this S formula. And so this one will be better, so if you have t and n, even better. Okay. So those are 3 different ways that this one screen, Cohen's d to independent t, can calculate. So if you only have t and degrees of freedom, it'll give you a number. If you have t and the n's, even better. If you have t, n, and the standard deviations, that's the best. What happens in the Hedges G window is that it is a correction on Cohen's d. So the top is actually the same. It's calculating the same independent t1 with either one of these three formulas, and then estimates the correction value. So you have to have the ends for this one. And so this is the correction supplied by hedge and or hedges, and so it will apply that correction. And so you'll see in this window it gives you what the correction value is. Last but not least, there's glasses delta, which is used for designs where you have a control group. And so you've got control versus experimental group, which is sort of your like classic statistics example. And so this the two means divided by only one of those standard deviations. So when you have glasses delta, you have to enter the control group first, I believe. So let's do an example. And this unfortunately looks a little crazy because there's a lot of different output. But starting with independent t here. And so resize my window just a little bit, squish it up so we can see everything. In the SPSS output, your two different n values, which we made them equal, my two means, my two standard deviations, would be the best way to do this. So I got 6 versus 7.53. My two standard deviations, 2.50, 1.76. Okay, we'll auto-calculate standard error, but I don't have the right ends, so I'm going to have 32 and 32. And that gives me the correct degrees of freedom down here, n-1 plus n-1. And it actually calculates t. So t is pretty close, 2.83. And it calculates the pooled standard deviation for you, which is so great because that is nowhere on any output ever in SPSS. And the standard error, which I can check against the standard error difference down here, 0.54. If I'm looking at SAS, here are my means, my standard deviations, or standard errors, and right here, so it's laid out very similarly to SPSS, and it gives you the means again, and it actually does give you the pooled variance somewhere in here, 2.61, there we go, 2.16. And so that's nice about SAS is that it does actually give you the pooled number if you had wanted to calculate Cohen's d by just looking at this. This actually makes it much easier because it gives you the mean difference and standard deviation. Bam. But if you didn't know that's what that was, it would be hard for you to do just looking at the numbers that you have. Okay. So that's one way to do it. I can also calculate directly from t all by itself. So let's see here. I've got 2.83. Where are you going here? Oh, I didn't click on it good enough. There we go. And so it gives me another number that's pretty close, negative 0.72. And you'll notice how that cleared everything out. And that's going to calculate from t's and my n's. If I don't have this at all, you do have to get it estimated to get to degrees of freedom. So I can't type down here because this is derived. And so in a study, we're hoping that people have at least reported how many people they have in each group, and then you can look at the degrees of freedom. I hope they match. But let's say you have t of 62 equals blah, blah, blah. What you can do is just sort of estimate how many people are in each group. It's not the best way, but it's pretty much your only option. So I could estimate 32 and 32 because I know there are 64 people because it's n-2 to get to degrees of freedom. But if you know that, oh no, instead there were 30 people in this group and 34 in that group, that would give you a better number. So of these, this one is sort of the least accurate number, more accurate with this formula, and the most accurate with this formula, this one here. Okay. Now, if I go to measures and click hedges, oops, I clicked out glasses, hedges G, it's actually going to do the same thing for me. So let's calculate from T to speed things up. So I'm going to say I got 32 people and 32 people, I get negative 2.83. And now I have corrected that number to be 0.71. Okay, so the correction doesn't make a huge difference because this is fairly, I've got enough people for it to be normal. I've got 30 people, and the hedges correction just lowered it a little bit. So it's Cohen's d times this correction factor. So it's actually correcting for unequal sample sizes and it's a little bit of non-centrality. So let's make this 30 and 15. Oh, that should have changed. That would have changed. Oh, I would need all my other numbers too to make that happen. But hedges does apply this like correction to the different values. If I do glasses delta instead, you do need the means. You can't really do this one from t. That's why t has moved down here. So let's see. I've got 6.0, 7.53. My standard deviation's 2.5. I'm going to enter group 1 as the control group and 1.75. And then I've got 32 and 32. So you actually don't even need this number. Okay, so I could make a 0. Okay, that actually will freak it out. Sorry. So 1.76. Because it is calculating based only on one of those standard deviations, and you should make your control group standard deviation or standard deviation 1 the one you want to use. So those are all the different types of independent t calculations, for example, for different Cohen's d, hedges g, glasses delta. So they're all variations on a theme of the z statistic. And then, let me scroll some more. Let's talk about the dr window. Okay. R is its own measure of effect size, but let's say you were trying to calculate a meta-analysis and you wanted everything to be in D, and you wanted to use confidence intervals based on D and not R. Okay. Because confidence intervals for R are based on centralized distribution. So I could enter that correlation coefficient, and it will calculate a backwards translation of D using this formula. If everything is already in R, don't translate to D, because it's just another type of test of effect size. But if everything is in D and you want to go backwards, you can. So in SPSS, I'm going to enter 0.451. Okay. And N. Always need N. So 50 here. Okay. Now, one problem is that sample size DF appears to be wrong, so we'll get that fixed. It should be N minus 2. Right? Okay. And so it calculates the test statistic for you of for T that you don't ever normally see with SPSS, and then it gives you the correlation coefficient here in SAS, and it tells me what R squared is, so 0.451 squared, and then here's Cohen's d right here, and it's calculating based on R up here with this formula. So the Cohen's d is correct, even though our little degrees of freedom number is not at the moment, because it is based on R squared here only. And so one problem we have is that apparently our upper and lower limits are acting funny. And so MOTE's still in progress, and one of the things that we're trying to work on is moments like this, where you have an upper and lower limit that don't make any sense. And so if you get that sort of thing when you're working with the program, please send me a screenshot, and I will get on it and figure out why it is not actually calculating around the upper and lower max. Okay. But that's how the program works. Okay. The other options, eta, partial eta, omega, and the interclass correlation coefficient are still kind of in progress. They will run for you, but they have a lot of funky moments where they will not be the right kind of confidence interval, especially eta. We're still trying to work on the fact that it's asymptotic. It cannot go over 1, and so sometimes it'll estimate the upper and lower limits outside the range of your effect size, which is a little silly. The odds ratio one works just fine. It's for a 2 by 2 chi-square table, especially if you're doing sensitivity and those sorts of things. And so you could enter all of your numbers from your table just to make one up, and it will give you the odds ratios for those, and the confidence interval around that. All right, So that is how you use Moat. Just some general procedures. Please know that it's still under works, but everything from Cohen's D here to Glasses Delta has been tested extensively and works fairly well. Minus this degrees of freedom issue up here, which I will get fixed quickly. Everything here is still kind of under testing procedure, so use it at your own risk.